Hi everyone. I'm Jason, co-founder at Dyna Robotics. We also brought our cute robot dinosaur. I'll tell you a little bit about what we are showing here later. So today I'll talk about high-performant and robust generalist policies for robotic manipulation. So let me first introduce our company, Dyna. So we started the company last year, September 2024, with the core thesis of focusing on developing robust foundation model autonomy in the real world. So we focus on developing general manipulation, purpose manipulation system on our robots. And the way we do this is by combining frontier research that we do in-house plus commercial deployment that we put out to the field. And in the next slide, I'll talk about why that's really important. And recently, just as of last week, we raised our Series A from a lot of great places that give us money to help us achieve our mission and accelerate our progress. So at Dyna, we do frontier research plus commercial deployment. And why do we do that? Because we believe that it's really important to combine research and deployment in a flywheel to make general purpose robots happen. So research can inform what can we commercialize on the commercialization of product front, but at the same time, only by going to deployment, looking at what people, businesses actually want in the real world, we can attain high quality data that match up to the production level quality that these businesses want, and also help us sharpen our research focus to determine what are the key technical problems our models have to solve in order to achieve commercialization. So just a quick background on the kind of models we're developing. So we're developing robot foundation models for manipulation. So at a very high level, we collect some robotics data. So in this video, it's me collecting some t-shirt folding data. Then we train a large neural network on many kinds of data and many different tasks. And then we have models that can do robotic control autonomously. So this is not a new concept. There's many great companies and many great academic papers doing this. But I think the status quo for robot learning from manipulation, especially robot foundation models, is still not a bit as close as we want it to be for real commercialization. And the central problem facing the field is, as I stated here, which is that all these foundation models are very flashy, putting out cool demos, but they're actually not super reliable to be deployed in the real world. But on the flip side, you can develop specialist models for specific tasks, but the software stack you develop for these specialist models aren't very scalable. So at Dyna, our core mission on the research and the software side is to develop high performance and robust performing general purpose models that can power our robots to do many different kinds of tasks in the real world. So in order to achieve this mission, what are some of the core research problems and technical problems we're focusing on right now? So the first one is actually just be able to train models to master many complex tasks very reliably, such as folding t-shirts. And the second is to enable models that have these skills to be able to generalize to environments it has never seen before. This is very important because you can imagine your model can do many things. If you want to deploy to a new customer site with a very great success, the model has to be able to generalize. And finally, every single deployment will not be perfect, will not work 100%. So it's really important we also have techniques that allow models to learn from their own execution, from their own experience. So for the rest of the talk, I'll show some research highlights and results we have developed over the past year since our company's starting. And the first thing I'll talk about is this live autonomous demo. So at Dyna, we really preach putting performance out of the box. We want to develop robots that just perform, that just do the task without any training. So what you see here is a robot that we brought from our office from Redwood City. It took 20 minutes yesterday to just set it up. We didn't do any on-site data collection. So for this model and this robot, it's the first time it's seeing SF Jats, seeing the audience. Many of the audience members are actually in the camera's viewpoint. So everything is zero shot, right? The model is not specifically trained, and it's trying to do very complex tasks of end-to-end t-shirt folding, back-to-back. And since the talk started, it's already folded 2 t-shirts very nicely, and it's progressing very nicely to the third one. And so for the rest of the talk, I'll just let this live demo just keep running, and at the end, we can count how many shirts it's folded. And at the same time, on the slides, which you might also want to pay some attention to, I'll talk about some other high-level model capabilities we're also developing in-house. But it's okay if you just want to watch the robot, that's totally fine. Yeah, that's more important. Yeah. All right, so performance out of the box. What are some other things we're developing? So recall that we're not just trying to solve laundry folding. We're also in the lab developing capabilities for many different tasks. So the first one is, we're teaching our robots to use tools very reliably. So here's a robot that can use a real knife and a chopper to, just continuously chop celery nonstop. So here is the first celery chopped, and as the video progresses, it's just gonna keep going, grab the next one and go. And for all of the capabilities we instill in our model, we want it to be really high reliable and very fast. So it's just gonna keep going. But in addition to making model being able to use tool, another thing we really care about is getting the model to be able to do very precise tasks. So here's a more magic trick kind of task. We're also teaching the same model, right? So this is cup stacking. And the cup stacking is actually very hard if you have tried it yourself, because all the cups need to be precisely placed in relation to each other. And if the robot gripper isn't grasping the cup just with enough force, you might accidentally grasp many cups from the stack, and then that would destroy all the progress. But what you see here is the model being able to reliably do the very precise task over and over and over, just to show the high performance generality we're trying to get our model to do. And at the same time, we also have trying to get the model to not just do some repetitive tasks like the first two, but really long horizon sequence of many different subtasks combined. So here's the placemat preparation task where we are teaching the model to, here's flatten a napkin and fold it nicely, and then you would try to place the napkin on a placemat. And I'll just let you watch the video to get what's really going on here. And finally, also something like making and serving breakfast. So all of these share the same architecture. They're all trained from the same model. We have figured out many effective recipe for putting all these skills into the same model. And for all of the tasks I'm showing you here, they have used less than 10 hours of data. So it's actually very efficient, which just a day or two of data collection, we can get to this level of performance. So you can see the napkin there is folded very, very nicely, neatly, like how a human worker would fold it. And then the robot would continue. And at the bottom right, we also have taught a robot to deliberately wait for the bread to be toasted and for the coffee to be made before it executes another action. That might sound actually fairly simple and trivial, but typically foundation models like this would just keep trying to do something, but we have taught a robot to deliberately stop and wait. And at the bottom left, you see the model is able to put the fork and a knife very nicely into the napkin it's folded and then complete the task, right? So here I'm just showing you a variety of tasks we have taught our model to do and to be very general and highly performant. And I think another thing that's fairly important for these generalist robots is the ability.
Hey, Tyler, can I have a Butterfinger, a Kit Kat, and a Twix?
Right, the ability to follow precise language command and fulfill them. So here's a demo we did in office where the robot can listen to free-form language commands from many different Dyna employees and give them candies.
Can I get a Reese's and 2 Kit Kats, please?
Yes. So it's able to fulfill, open-ended language command, especially in relation to having to count how many candies. So this requires the model to have some sort of memory to be able to do.
A couple of Butterfingers. And can you add 2 Kit Kat for me too?
Right. So here a person interjected in the middle and added extra candies to the task, and the model can change the task it's trying to do and fulfill. Right.
Can I get
so we do this for 5 employees in a row, but for the interest of time, I'll skip ahead to show that the capability is actually very robust. Right. So here.
5 Butterfinger.
So in these cases, after the commands given, the employee would try to shuffle the basket in many different locations, and the model can still follow language very well to fulfill the command. Just to show the ability to get both language following and a general and a robust manipulation into one system. So all of these are very distinct and interesting capabilities that we're putting into our model. But if you actually think about trying to commercialize on any of these tasks, what's really important and has been missing in current dialogues for a generalist model is how can we train these models to not just be putting out fancy demos like the ones I'm showing, but getting them to 100% robust. Because if you think about a real customer, they're not going to take a model that's only 80% success rate. They want something that's reliable, that they can trust. So we released a blog post around June of this year on our breakthrough results of training a foundation model, large vision language action model, that can actually achieve something very close to 100% success rate on a production-ready, difficult task. So the case study that we studied is the task of folding napkins. So if you go to any fancy restaurants, there's a lot of napkins that need to be folded on a daily basis. And that was a good commercial task for us to simultaneously think about how to deploy our robots and also get our models to be very capable. So that's what we did. And with Dyna 1, we shipped a foundation model that's able to fold more than 850 napkins in a 24-hour non-stop, non-cut continuous run with 99.4 success rate. And the only failure cases is when the model pulls the napkin too hard from the stack, so the napkin falls onto the table. And here we sped up the video a lot because it's 24 hours. We couldn't fit that in this talk, but you can see the clock moving. And my favorite part is right now, actually, when the outside changes from dark to day, right? Just showing how much time has actually transpired. And this is not just a single occurrence. We're able to repeat the 24-hour run 4 times within a single week, just to show how robust we can get these large foundation models to be performant. And so that was very interesting. And of course, we ran some baseline for this model as well. And before that, I just want to spend some time talking about why this was really difficult. And as I was talking, we folded a stack of 7 T-shirts, so the stack is getting too high. So I'm going to just move this stack over so this can continue for the rest of the talk without me intervening. You can look at the quality of the shirts later. They're actually, I think they fold better than I do. So yeah. Yeah, so continuing on the napkin folding, right? So why is this task particularly hard? So you see, if you want to grasp a napkin from the stack, it actually requires very, very precise motion. And almost all the failure cases is when the grasping was not accurate, so we pulled out many napkins. And if you actually want to ship production level napkins, the difference between a grade 5 napkin, which is what the customer would accept, versus a grade 3, is only 1 centimeter of difference. So being able to get these learning-based methods to be that precise has actually been a huge challenge in the field, right? And for that reason, when we initially attempted this task, we trained the model using the standard vision language action model, pre-training plus post-training recipe that's very popular in the academic literature. And what we found is that, yeah, this model can get to about 80% success rate. But if you think about a model that's 80% success rate, yeah, I think that's good enough to put out a demo. But if you want the model to do 100 napkins in a row, then the chance is almost 0. So you can see a time lapse of the model gradually messing up and drifting out of distribution. So clearly getting to that level of robustness that we showed in Dyna 1 is very challenging and very hard. So how do we do it? What are some of the technical things we did to make this happen, right? To make this kind of generality robustness happen. So one thing that we've been developing at Dyna is this model class called reward model. So this is a model that's not outputting robot action, but rather can watch a robot video of the robot doing the task and just precisely measure the amount of progress the model has made towards the task. So we trained this model to be able to score progress for napkin, for t-shirt folding, for a bunch of other tasks using the same kind of algorithm. And with the reward model that can really precisely score the model's progress, then you can imagine we can just train a base model that has some level of success rate and just run the model on its own to collect a lot of data, and then use this kind of model to score good trajectories and discriminate out the bad trajectory. So we can just have the model continuously run and learn on its own outcome. And here's the second instantiation of the reward model. So here you see the model is autonomously folding napkins on its own, and we're able to predict which step of the task the model is at, and also output the task progress, right? And this is very important because you imagine when your model is reasonably good, then most of the trajectories as it's doing are pretty smooth and going forward pretty well. But occasionally, right now, you'll see right here, the model is messing up. So traditionally, if you want to know that the model is messing up, you might need a person to just like supervising the robot standing there, right? But with this model, we can automatically just let the robot run and score its execution and directly just filter out the good trajectories versus the bad trajectory, allowing the robot to learn from its own without too much human supervision. Right, so here I'm just gonna show some highlighted results, which is like the most interesting part of all these 24 hours run that really highlight the kind of robustness our model has to get to the level of success rate that's hasn't been demonstrated. So in here, you see the model actually grasp a stack of 10 napkins, right? Because it wasn't really precise. And then it's able to put all the extra ones back, continue on the current one on the table, and then be able to singulate all the napkins that it mistakenly grabbed again and continue, right? So you see here, it's like separating the napkin and being able to recover from all these mistakes. And here's another instance that I manually filtered out from the 24-hour raw footage. So here's what happened. The model accidentally grabbed the entire stack. It realized I was trying to put them back, and it's able to get a single one. And then it's really be able to grab more napkins, fix the messy stack, and just continue, right? And during our initial data collection to get the task doing somewhat well, we never collected data for this kind of mistake handling. Right? As you can see, this is a very out of distribution, but the model can continue. And finally, like I talked about Dyna, we combine research and production at the same time. So here's the model running live at a real restaurant in Los Angeles, folding napkins. As you can see, like we actually just took up the no storage area in the restaurant in the back office, just folding napkins. Yeah. So this is some of the technical highlights we had over the past year of building the company. What are some of the open challenges that's remaining? I think there's a couple. First of all is model evaluation. Right now, we evaluate all of our models by running live on a real station, like right now. Like this is a valid evaluation run, right? But once you have models that's really good, like for instance, we have a model that's 99.5% success rate, another one that's like 99%. In order to get statistically significant difference in the results, you actually have to run hundreds of trials in the real world. So how can we discriminate good model versus a better one without running online eval? That's actually a very thorny question that we're trying to answer today. And the second thing is that, our results, we got all of our results by collecting our own data where we ensured very high quality. But there's a lot of low quality data that you can find on the internet, such as human videos, egocentric videos of humans doing things that may or may not help the robots. So how can we combine this more abundant source of data that's more low quality with all the high quality data we have to get the model to be able to jumpstart on a new task even faster? And finally, when we are at deployment site, of course, you don't want a Dyna employee there to babysit the robot, especially as we scale. So how can we enable few shot improvement? Meaning that just by collecting a little amount of trajectories at the real customer site, we can get the model to work very well. So these are some of the very interesting challenges we're trying to solve at Dyna right now. And finally, so we raised our recent round of funding, announced last week. We're actively growing and hiring. We're hiring across research, software, hardware, also business operation roles. So if this sounds interesting to you, you can apply online, or you can also find me after the talk. I'm happy to chat. And we work very hard at Dyna, but we also try to have a lot of fun. So here's, we taught the same model that I was showing you how to play mini golf, right? So that's one of our employee. And here's our robot doing the mini golf. Yeah, our robot's, kind of competitive. So, right. So, as we are growing our company, we're also very interested in doing more community events. So this week we actually have a happy hour in SF. So if you're interested, scan this QR code as well, and we're happy to see you and talk to you more there. So, so that concludes my short presentation, and thank you for listening. Thank you. And just want to mention, as the talk went on, I think the model just continuously folded a lot of shirts. And you can check the quality a little bit later. And Okay, I think that's all. Thank you.